Okay, we're going to be talking about another series test, and this one is the alternating series test. So let's talk about what in the world an alternating series is. All right. Well, if you think about it, alternating it means in terms of sign, positive or negative, positive or negative. So I'm just going to give you a rough illustration. Suppose that I had something like 1/2, let's say minus 1/3, plus 1/4, minus 1/5, and so forth and so on. Okay, so this is what we mean by an alternating series. So what we're going to do is we're going to investigate the convergence of this, and then we're going to lead into something called absolute convergence. So we're going to talk about both in this video. All right, so it may be long, so I'm just warning you now. All right, so if we look here, we've got some series a sub n, and a sub n is this -1 to the nth times b sub n, all right, or -1 to the n plus 1, b sub n. So all that does there is just changes whether your first term or your second term is positive or negative, all right? So what we're going to do is we're going to examine just the b sub n part, all right, just the b sub n part for this alternating series test. So the first thing that we want to say is that the elements of b sub n should be non-negative. All right, that is, they should be greater than or equal to 0. And then when you look at this other series component, it's that the limit of as n approaches infinity of b sub n should be 0. All right. This does not mean that the sum of this series is 0, so much as the sum of just this component-wise portion, b sub n, should be 0. And then lastly, b sub n should be a decreasing sequence. All right, so b sub n should be getting smaller as things progress, as your n gets larger and larger. So if these three conditions are met, we can say then that the alternating series a sub n converges. Okay, so let's take a look at the first example here, or really the only example of this type. And we're going to talk about -1 to the n plus 1 over n. All right, so let's discuss what this looks like. If I'm considering, suppose n equal 1, and so I need to write that in. Let me just correct my pen color. N equal 1 to infinity. All right, so I have -1 to the 1 plus 1, that's -1 squared, so this gives me a 1 over 1, 1. All right, now I plug in my 2. 2 plus 1 is 3, so that's going to make it a negative in the top. So minus -1 over 2 plus, now I plug in a 3. 3 plus 1 is 4. -1 to the 4th is a positive 1. So plus 1 over 3, and so forth and so on. So you should start seeing the pattern of this alternating series. All right, so it follows that. All right, so what do we know? Well, let's pluck this apart. A sub n is this -1 to the n plus 1 times 1 over n. Well, let's examine our b sub n. This right here is our b sub n. This right here. And that looks familiar. If you remember something about something called the harmonic series in a previous video, that's quite interesting. But let's go ahead and check. Okay, so we know that it's the elements of b sub n are positive, okay, because we're looking at not the alternating portion, but you know, we're looking at 1, we're looking at 1/2, 1/3. They are definitely all positive. All right, now let's check the limit. So the first condition is for sure met. All right, so these right here are positive values. All right. Secondly, so that's the first condition. Second condition, the limit. As n approaches infinity of b sub n. All right, what does that look like? Well, this is the limit as n approaches infinity of 1 over n. Well, that's for sure is 0. 1 divided by infinity. I mean, when you think about $1 and divide it amongst, I don't know, 1 billion people, each person's going to get relatively nothing. So the first condition is met. The second condition is met. Now we check the third and final condition. And the third condition is that B sub n, all right, is a decreasing sequence. And that is actually true. All right, think about it. We had 1 followed by 1/2 followed by 1/3 followed by 1/4. So yes, they're getting smaller and smaller. So this condition is met. It is decreasing. All right. Okay. What does that mean here for us? What that means then is that the series a sub n from 1 to infinity, all right, is...
Until next time.
Okay, that shouldn't have happened. It is, let's write this out again. It is convergent. It converges. Okay. So what I want to make a point here is saying that if you make the harmonic series are alternating, you'll make it converge. So it makes the harmonic series converge. All right. So it's an interesting way to look at the harmonic series, really. If you make it alternating, you can actually make it convergent. Okay? So now, what we're going to do next is we're going to talk about something called absolute convergence. So take a quick pause, rewind if you have to, and we're going to come back with the absolute convergence. Okay, so now we're going to talk about absolute convergence here. And we're going to piggyback off of what we just learned here as well in the first example we're going to look at, or in the only example we're going to look at here from here on out. So a series A sub n converges absolutely. That means it is absolutely convergent if the corresponding series of absolute values for A sub n converges. So notice the whole thing about absolute convergence is that you're taking the absolute value, okay? So that's the whole picture about this, all right? A series that converges but does not converge absolutely is said to converge conditionally, all right? So think about the last example we just did, the harmonic series. We know the harmonic series diverges, but it converges when we make it an alternating series. So that's why I say see previous example. So rewind and go look at that one more time if you need to. But now let's dive into a theorem. And this right here is what we call the absolute convergence test. And it says that if the series, if you take the absolute value of a series and it converges, then the series itself should converge. Okay? So let's take a look at this example. We have negative 1 to the n plus 1th over n, times n over n squared plus 1. All right, definitely an alternating series here. All right, so what I'm going to do here is I'm going to take a look and apply the alternating series test, first of all, because I know that this is alternating, so I can determine, well, does the alternating series converge? Let's find out. Let's examine this portion right here. All right, so if you remember anything, notice that this a sub n, all right, and I'm going to write it out like this a sub n is made up of this negative 1 to the n plus 1 times some b sub n component. And this right here represents our b sub n. And that's what we're going to examine here when we apply the alternating series test for this first part. All right. So we're examining b sub n equal to n over n squared plus 1. All right, so we examine that. Let's see, what do we need to know? Well, I think the first thing we said was that it had to be positive. And I think that you'll find that as you go from 1 to infinity, these, of course, are all positive values. All right, so let's consider what b sub n looks like. All right, it's 1 over 1 squared plus 1. So the first element there, 1/2. Followed by 2 over 2 squared plus 1, so that's 2/5. Followed by 3 over 3 squared plus 1, so that's 3/10, and so forth and so on. All right, so what can we say about this? Well, I'm going to make the claim, and it's not so much a claim as an assertion, that this is indeed decreasing. So it is decreasing here. All right, so that's one of the conditions that's met. But the other condition is that they are definitely positive values. So I will put a check mark next to that as well. They are positive. All right. So now what I need to do is I need to lastly find the limit as n approaches infinity of n over n squared plus 1. Now, I can't readily plug in infinity, so what I'm going to tell you to do is, if you remember anything about limits and what you can do with these limits, that is that you can apply L'Hopital's rule. So I'm just going to apply L'Hopital's rule just to quickly take the limit, and I get the limit then as n approaches infinity of 1 over 2n. And now I can plug in infinity. I get 1 over 2 times infinity. Well, that's just 0. 1 divided by something insanely huge is 0. So we have met the conditions here. And let me switch pen on you. Let's see here. I was using green. We have met the conditions for the alternating series test. All right, alternating series test. So what can we say about the alternating series? All right. For the alternating series, a sub n, it converges. All right. It converges. All right. But now let's discuss absolute convergence, okay? Because we're talking about absolute convergence. The alternating series converges. Now we have to consider the absolute value. All right, so let's take a look. We're going to use this basically the same thing here. All right, so we're going to go from n equal 1 to infinity. We're taking a look at the absolute value of this, negative 1 to the n plus 1 times n over n squared plus 1. We look at the absolute value again. Okay, what do we get? Well, it's just something similar to what we had before. All right, n over n squared plus 1. But I need to make the distinction. Before, we were just looking at the limit of some sequence, okay? We were looking at the limit of the sequence of b sub n as n approached infinity. Here, we are actually examining a series, n over n squared plus 1 from 1 to infinity. So two little different things. While it may sound and look the same, you may find that we're coming to a different conclusion right now. So what we're going to do is we're going to take this right here and we're going to do direct comparison. All right, what are we going to compare it to? Well, if I think about power reduction, I have n over n squared. I think it's probably best to compare it to something like 1 over n. All right, so let's say n equal 1 to infinity. 1 over n, all right, is what I want to compare it to. Okay, so let's see here. I know something about this 1 over n, all right? And I can list out the elements if you really want to see them. These again are 1/2, this is 2/5, this is 3/10, and so forth. All right, this one right here is, let's see, 1, 1/2, 1/3, and so forth and so on, right? And I know for a fact that this right here diverges. All right, why? Why does this diverge? Because this is the harmonic series. All right, this is harmonic. All right, let's see. What else do we need to know? Well, the other fact I could probably state is that this one is bigger in relation to the other because the numbers are just naturally larger. All right. Okay. So I take a look at this, right? And I see, okay, my direct comparison's not going to work. All right. So I'm comparing them, but direct comparison doesn't work because the bigger one obviously diverges. The smaller one doesn't mean anything, right? So we have to use some other method. So what I can do is I can do the limit comparison test. And so this, if you recall, is the limit as n goes to infinity of a sub n over b sub n. Basically, you're finding like the ratio of the two. All right. And if you know, if you get something, a limit that's both positive and finite, then you know that it will either converge or diverge depending on what it is that you know. In this case, we know that 1 over n diverges. And we compare n over n squared plus 1 to 1 over n again because n over n squared reduces to 1 over n. Okay, so what I'm going to do is I'm going to write out then the limit as n goes to infinity. All right, the limit is n goes to infinity, and I can say n over n squared plus 1 divided by 1 over n. And so let's see what I get. All right, I get the limit as n goes to infinity of n over n squared plus 1 times n over 1, which gives me the limit as n goes to infinity of n squared over n squared plus 1. Okay, and from here on out, we can just divide out the n squared. All right, so what do we get? this becomes a 1. That becomes a 1 as well. We get the limit as n goes to infinity of 1 over 1 plus 1 over n squared. Now we can evaluate at infinity if we pretend that. Okay, this is 0. All right, so you're left with 1, which is both positive and finite. Okay, therefore, we can say that this series, negative 1 to the n plus 1, let's see, times n over n squared plus 1 does not converge absolutely, all right, because this would have to diverge based on the limit comparison test. So we can then say that this series, all right, a sub n, there it is, a sub n, converges conditionally. It converges conditionally. So that's what we're getting at here, is that it converges conditionally based on what we have found and identified here. So maybe a rather long-winded video here for you, but as always, I hope this video was helpful. And remember, like and subscribe.